For the introduction. So today, let us talk about the Gaiotto conjecture. To start with, let us first fix some notations used in this talk. We let G be a reductive group defined over C, the complex number field, and we denote by F, C bracket D, the Lahom power series, and we denote by O, the formal power series. Given group G, we can consider its loop group, denoted by GF. And also we can consider its outgroup, denoted by GO, which is a subgroup of GF. In this talk, the geometric object that we will often meet, it is the affine Grassmannian, which is defined as the quotient of GF by GO. I mean the group quotient. And we denote it by G. The Grassmannian G, it has a formally smooth in the beam structure. So in particular, we can consider the D module on site. And we denote by D G, the category of D modules the Grassmannian. Okay, so that is our, these are the notations. To start with, let us introduce the hyperspherical variety. Given a G Hamiltonian symplectic variety M, we call it to be hyperspherical. If it satisfies the following condition, I mean the field of G invariant functions on M, it is Poisson commutative. And maybe with some other technical assumptions. For example, usually we need M to be affine, and we have some conditions on the stabilizer. There is an important class of hyperspherical variety. It is given by
what does it mean, hyperspherical?
Sorry. Hyperspherical means the field of G invariant rational functions on M is Poisson commutative.
Yeah, first of all, it's symplectic.
Yes. Yeah, it is a G Hamiltonian symplectic variety for G.
And the action also is symplectic. Hamiltonian.
Yes. Yes. Yeah. There is an important.
То есть многообразие сравнительно маленькое по сравнению с группой. Еще эквивалентное определение, что типичная орбита коизотропна. Почти все орбиты коизотропны.
And there is an important class of examples of hyperspherical variety, which is given by the codiamond bundle on a spherical variety, or more general, a twisted codiamond bundle on a spherical variety. So here, your X is a G spherical variety. So maybe let us recall the definition of a spherical variety here. Maybe here. Okay. For a variety X which has the action of G. We call it to be spherical if X has an open parallel orbit. B means parallel for G. So you can regard it as a non-abelian generalization of toric varieties. There are some examples of spherical variety. For example, first, as what we just said, any toric variety is spherical. The example is, for example, you can consider the action of Gm on A1. It gives rise to an example of a Gm spherical variety. And the second case, it is symmetric variety. For symmetric variety, we mean first if you have group G and you have an evolution on site.
GM is the multiplicator group of the field.
Yes, yes. And you have a group G and you have an evolution on site. You denote by H to be the evolution fixed subgroup. And then you consider the quotient space, G quotient H. There is action of G on G quotient H, which is given by left multiplication. Through this way, you can get a G spherical variety. For example, if your G is GRN, and you take your H to be ON, then it gives rise to an example of a GRN spherical variety. So that is the example of a symmetric variety. And there are some other cases of examples. For example, you can consider a point, and you can consider the action of G on site, which acts triplet. I mean, obviously, it has an open B orbit, which is itself. So through this way, you can get a G spherical variety.
So why symmetric has an open Borel orbit? It's obvious.
It is some theorem. It is some theorem. I've got to prove it. Well.
Winberg.
Yeah, maybe I forgot. Sorry, I forgot to prove it. Yeah.
Knop Winberg.
Yeah, and also.
Есть примеры, которые не один. So is there any examples besides like?
Вот мы сегодня будем изучать.
Okay.
Yeah, and also you can consider a group. I mean, for any group G, you consider the action of G times G on site. One acts from left and another from right. And through this way, you can regard G as a G times G have a spherical variety. And there is another example that I want to introduce here. Given a reductive group G, then you take its maximal unipotence subgroup U. Yeah. Then you have action of G quotient U, which is given by lateral multiplication. And by the brutal decomposition, there is an open B orbit in G quotient U. Yeah, so through this way you get this one, it is a G spherical variety. So as what we said just now, if you consider all these spherical varieties, and then you consider the cotangent bound on side or the twisted cotangent bound side, you will get a hyperspherical variety. And actually, in this talk, we will mainly meet the following case. I mean, the following case is very important for us, where your M, your hyperspherical variety, it is of the following form. It is a twisted cotangent bundle on a homogeneous G spherical variety, G quotient H. Here, your H, it is a subgroup of G, and your C, this one, it is an additive character of H, from H to A1. So this one you can divide it like this. First, you consider the cotangent bond on G, and there is action of H on site.
What is a twisted tangent bangle?
I'm going to define it. Yeah, sorry.
Потом редукция. На нуле.
Yeah, so you consider codarium on G, there is action of H, and then you consider Hamiltonian reduction. So we refer to the curve of C. So that is your twisted codarium here. In this talk, we will meet many hyperspherical varieties. But to start with, let us just mention 3 easiest examples of hyperspherical varieties. Okay, so the first case, let us consider this one. G acts on the point. Because G acts on the point, so the codarium bundle on the point, which is itself, it is a G hyperspherical variety. And we call this case to be the point case. And also you can consider this one, the fourth example above. You have an action of G times G on T star G. Through this way, you can get a hyperspherical variety for G times G. And we call it to be the group case. And this group case, it is a case of a relative Langlands problem, which is closely related to the geometric Langlands problem. And the third case, it is the fifth example above. Here you consider G quotient U. You notice that there is a non-degenerate character for your maximal unipolar subgroup U. For example, if your G is G of N, then you can take your U to be the group of our triangular matches. Then your character of C, you can take it to be the sum of elements in the subdiagonal. So that gives rise to a character of C, which is non-degenerate. So through this way, we get a twisted codarium bundle on G quotient U, and it is a G's hyperspherical variety, and we call it to be the Whittaker case. Then let us mention the hyperspherical S-duality or S-duality. The S-duality, it conjectures that there is a duality between G hyperspherical variety yes, but maybe inside there is duality. Yeah. There is a bracket outside. Yeah. There is a duality between this one and the hyperspherical varieties for G check. Yeah, so it goes from M to M check. Here, your G check, it is a Langlands dual group of G. In general, how to characterize this duality, it is still difficult, and people don't know how to contract the hyperspherical duality. But in these three examples that we mentioned here, people already know them very well.
So you mean that there is no canonical way to construct the dual variety and only?
Yeah, and then it should satisfy some conditions, some properties, and we will mention some one property later. What does it should satisfy?
Ну, да, при определенных ограничениях есть некоторая, значит, конструкция двойственная многообразие, но она очень заумная. Через какие-то кольцевые объекты в каталоге категории Grassmannian. Но, например, очень доступны и красивые.
Yeah, the interesting thing is the speaker don't know what is going on. Where are we? Yeah. We are trying to mention these three examples. So first, examples of actuality pair. The first example that we consider here, it is a group case that we mentioned here. The group case, it is self-due. Namely, if you consider G times G on T star G, then its hyperspherical due. It is given by M check, which is given by T star G check. And the cotangent bundle of the Langlands two group. And here you regard this guy as G check times G check hyperspherical ID. So that is the first example of this duality. And also there is another case. There is another example that we consider in the William case here. Then you have a G spherical ID, T star C, G quotient due, and its hyperspherical due, it is actually given by the point. And you regard it as a G check hyperspherical right. So from this example, you see that even for the most trivial case, its hyperspherical due, it is already something which is not so trivial. So you can imagine that for the more general due, the construction of due hyperspherical writing, it will be more complicated.
Where is C there on the
Sorry. It is here. It is a non-degenerate character of U. U it is maximum unipolar subgroup.
No, he means on the right of this duality. There is no psi for the point.
Really?
All the psi are conjugate, so there's no choice. It's okay.
Okay. Yeah.
It's not degenerate.
Yeah.
So it doesn't it's as most to the product of G, but the classic
Рома говорит, что в случае ЖЛН это скручено красное растворение, это прямое произведение той же самой ЖЛН и N мерного пространства. На равности физической структуры. И для других групп тоже аналогичная вера.
Yeah. So now let us mention the Ben-Zvi-Sakellaridis conjecture. Here for Ben-Zvi-Sakellaridis, we mean Ben-Zvi, Sakellaridis, and Venkatesh. Yeah, so the relative Langlands problem, it is a generalization of a geometric Langlands problem. So recall what does geometric Langlands want to do. You have some category or some object which is defined using a reductive group G, and then you want to find some relationship between some category or some objects which is defined using the Langlands group. So that is the geometric Langlands want to do. Here, for the relative Langlands problem, instead of using a group or its due group, here you should use hyperspherical variety and its due hyperspherical variety. So through this philosophy, the relative Langlands, the geometric Langlands program, it corresponds to the group case.
But you said you have a pair of Langlands.
Sorry?
In Langlands, you still have a pair of Langlands groups.
Yeah.
Corresponding subgroups.
And a pair of
Yes, so from GM, you have G check, M check. Yes. Yes. The BZ-SV conjecture, or the local conjecture of relative Langlands program, it considers the following thing. First, let us start from M, I mean the hyperalgebraic variety M. Then you consider its loop space. Know that usually we assume M to be affine, so you can consider its loop space, MF. Then we consider a structure shape on site, denoted by OMF. Then by some quantization procedure, you will get an algebra denoted by QMF. So in our particular case, where M it is the twisted codaric bundle on G quotient H, then QMF it can be thought as this, which is perceived twisted differential operators on G quotient HF. Here G quotient HF, it means the loop space associated with this quotient space. And people consider the module category of this QMF, and by definition, and by the above description, which is just the category of HF C equivalent modules on the loop space associated with G. So that is QMF mod. And people interested in the GO equivalent, GO invariant of it. I mean, denoted by QMF mode GO to be the GO equivalent modules over QMF. This guy, it is just by definition equivalent to HF the C twisted modules on the Grassmannian associated with G. Because here you have GO and here you quotient GO, then you get G. Interesting. Sorry, thank you. The BZ-SV conjecture, it considers the following thing. It claims that the category of HF, the C equivalent modules on the Grassmannian, it is equivalent to a certain G check equivalent quasi-coherent shift category on M check. But here we need to put some marks here, because instead of considering the G check equivalent quasi-coherent shift on M check, you need to consider its shared category. I mean, there are some homological shifting. For this category, you can also think it as follows. You consider the category of G check equivalent modules over a certain DG algebra. This DG algebra, it is given by the global functions on M check, but still you need to do some cohomological shifting. So that is the local conjecture of local conjecture of the relative Langlands problem. Instead of making this guy very precise, let us just mention some examples of BZSV conjecture in when we have S-duality pair. For example, recall here, we already have two examples of S-duality pair, and we put these two examples inside and see what will happen. The first example is the group case where you have G times G acts on T star G. So first, you have G times G acts on T star G, and this guy, it can be written as T star G times G quotient G, and to match the form written here. So here, so actually your H here, it is one copy of G, and your G here, it is two copies of G. So the left-hand side of this conjecture, it just says the category of a GF equivariant modulus on the affine Grassmannian associated with double G. It is the left-hand side, and by definition, this guy it is just equivalent to the category of GO equivariant modulus on the affine Grassmannian associated with one copy of G. So that is the left-hand side. The right-hand side of BZSV conjecture here. So your G check, it is, the right-hand side, your G check, it is actually two G check. G check. G check times G check. And the M check, it is T star G check, the cotangent bundle on G check. And you have some shifted by 2 in this case. And this guy, it is just equivalent to the category of G check equivalent quasi-Cohen shift on G check star shifted by 2. And it is equivalent to the category it is equivalent to the category of G check equivariant modules over the symmetric DG algebra associated with G check. But here you need to make the generator shifted by 2. Put the generators in cohomological degree 2. So that is the right-hand side. So then we can see that this the conjecture of BZSV is just as follows. The category of GO equivariant modules on G, it is equivalent to sim G check minus 2 mod G check. This conjecture, it has already become a theorem due to Buzou, Nikov, and Finkelberg.
And today is Mr. Government's birthday.
Yeah. So that is. So it is the first example of the equivalence that I mentioned today. Yeah. Okay. So yeah, let's write some cake here. Yeah. Okay. So this theorem, it is under the name of Dirac static equivalence. And it plays a very important role in the geometric Langlands program. So where are we now? Yeah, so that is the first example. You see that we still have, let's see the second example here. For the second example, our H, it is the U here, G, it is G here, put it here. So the left-hand side of Ben-Zvi-Sakellaridis-Venkatesh conjecture, it just says the UF with C equivalent modules on the Grassmannian associated with G. So that is the left-hand side. And the right-hand side of Ben-Zvi-Sakellaridis-Venkatesh conjecture, it is a quasi-co of G check equivalent quasi-convention on the point, which is by definition just the same thing as a category of representations of G check, of the Langlands group. So in this case, the Ben-Zvi-Sakellaridis-Venkatesh conjecture, it just says the category of UF, the C equivalent modules under G, that is equivalent to the category of representations of G check. This conjecture, it also has already become a theorem. It is due to Frankel, Ginzburg, and Wilden, under the name of geometric Kashoman-Shaleka formula. Yeah. So that is the Ben-Zvi-Sakellaridis-Venkatesh conjecture in the two examples of duality that we mentioned before. Both of the above two examples derive geometric static equivalence as well as the geometric Kashoman-Shaleka formula. They are very important for geometric Langlands program, but they behave very differently when we consider their deformation. It means when we consider the deformation of this guy as well as this guy, they behave very different. The first one, you don't have a visible or good deformation, but the second, yes. Here, for the deformation, we need the following thing. First, let us consider the Grassmannian for G, and we consider the determinant non-bundle on the Grassmannian for G. For any complex number denoted by kappa, we can associate it with twisting p delta kappa. And we can consider the category of a kappa twisted modules on the Grassmannian. Note that the determinant model P delta, it has HF and as well as HEO equivalent structure. So we can consider the corresponding twisted equivalent modules of the Grassmannian. That is to see for the category HEO equivalent modules of the Grassmannian, it has a deformation given by GO equivariant kappa twisted demodulus on the Grassmannian, and as well as for the UFC equivariant demodulus on the Grassmannian, you have a deformation which is given by UFC equivariant kappa twisted demodulus on the Grassmannian. However, here, the first deformation is not very meaningful. The reason is after you take deformation, this category will become too small, so it's a bit boring. For example, if your kappa is irrational, then the number of irreducible objects in the category of GO equivariant kappa twisted demodulus on the Grassmannian, that is just one. I mean, just have one object. Well, in the non-twisted equivariant category, there are infinite many irreducible objects. So through this way, after you take deformation, this category will become a bit, too small. Well, on the second, for the second example, for any kappa, the number of irreducible objects in UFC equivariant kappa twisted demodulus on the Grassmannian, it is still the same thing as the number of irreducible objects in the non-twisted equivariant category. So that means the second deformation, many objects they still survive after you take deformation. Yeah. So in other words, this deformation it is much more meaningful. So let us go back to our example here. Here. Yeah. So you notice that for the geometric Cauchy-Riemann formula, the left-hand side you have a meaningful, a good deformation, which is given by the category of UFC kappa twisted demodulus on some Grassmannian, and on the right-hand side, the representation category of the Langlands group. It also has a good, naturally defined deformation, which is given by the category of representations of the corresponding quantum group, right? So, and as you may expect, that these two deformed category, they are equivalent, and it has already become a theorem. When kappa is generic, or to be more precise, irrational, it has already been proved by Ginzburg. And when kappa is rational, yes, sorry. For here, the quantum parameter q and the twisting parameter kappa here, they satisfy the condition that q equals exponential pi I kappa. Yeah. So if kappa it is rational, it has already been proved by.
And kappa is an element of what?
Kappa it is So when kappa is rational, it has already been proved recently by Campbell, Dillon, and Ruskin. This theorem It is called the fundamental local equivalence in the quantum Langlands program, because it plays a very important and fundamental role in the quantum Langlands program. Yeah. Yeah. So now we can go to the Gaiotto conjecture. The Gaiotto conjecture, it actually corresponds to the quantum version of a Ben-Zvi conjecture. When admitting a reasonable or good or meaningful deformation. Yeah, so let us be more precise about what we mean here. Okay, for the hyperspherical duality pair, we have G and G check, GM and G check M check. And for the latter part of your Ben-Zvi conjecture, you consider the category of HF, the C equivalent modules on the Grassmannian. And you want to consider its deformation, which is the HF, the C couple twisted modules on the Grassmannian. It has a good deformation, means this deformation is good. To have such a good deformation, to have all the examples that we know which have a good deformation, it corresponds to some superquantum group, supergroup, GS. To be more precise, is this a basic classical supergroup GS such that G check, it is the zeros, it is the even part of your GS, and M check, it is the odd part of your of the corresponding superalgebra. And for the classical basic classical supergroup, it means it is of the following form.
Basic classical.
Yeah, basic. Oh, sorry. Yes, yeah, basic. Yeah. Basic classical supergroup. It means one of the following form: GLMN. I mean the general linear supergroup GLMN, or the also symplectic supergroup K2L, or G3, or F4. Or D21R. Maybe here we need to be more precise about what we mean by have a reasonable deformation. If you have a reasonable deformation, as I said, you want to have such a thing. It should satisfy the following conditions. The first condition that we want to see it is, first, this is a deformed category. First, it should be well defined. To make it well defined, you need to ask your determinant line bundle P delta. It has a HF equivariant structure. In other words, we can make it more precise. It means there exists a non-degenerate G equivariant bilinear form on G, which is trivial on H. Notice that H is a subgroup of G. So that is the first condition. Actually, this condition is already very strong. We don't have many examples which satisfy this condition. The second condition, it says after you take the deformation, the deformed category should not be it should not be very small. That means, roughly speaking, it means many objects they still survive after taking deformation. This condition is to ensure that the deformed category it is meaningful. This one, it can also be make it more precise. It means for almost all orbits which admits HF, which admits a non-zero equivariant module supported on site, it still carry a non-zero equivariant twisted module on site. And satisfy all these two conditions, all the examples that we know, they come from a supergroup and correspond to this case. So now let us see what does the BZSV conjecture see in this case. Or sometimes we also call it the implicit conjecture. It says the category of HF for C equivalent modules of Grassmannian associated with G, it is equivalent to the category of G0 bar equivalent quasi-coherent shift on G1 bar. G0 bar and G1 bar, they are shift. Or actually, this category it also can be defined. It is causal duality. It is equivalent to the category of representations of a GS underline. Here, GS underline means corresponding degenerate supergroup associated with GS. Let us recall the degenerate. What do we mean by degenerate here? Given any supergroup, super D algebra, GS, we can always define its degenerate version denoted by GS underline, which has the same underlying supervector space as your GS, but the supercommutators of two odd elements and is set to be 0. So through this way, you can define a new factorization algebra. You can define a new super Lie algebra denoted by GS, And here GS and N is the corresponding supergroup. So that is the BZ-SV conjecture C in the case when admitted a reasonable deformation. The Gaiotto case, the Gaiotto conjecture, it just corresponds to this BZ-SV conjecture when we consider the quantum analog. The quantum analog here on the left side, you deform it, and on the right side, you also deform it. The left side is the conjecture of Gaiotto. So we first require we couple a generic. Then the category of HFC equivalent couple twisted the modules of the Grassmannian. It is equivalent to the category of representations of the corresponding superquantum group, where Q and the couple is used to satisfy the condition where Q equals exponential pi couple. So that is the statement of a BZ-SV or an untwisted conjecture or under the Gaiotto conjecture here. So later, let us be more precise about what does this BZ-SV conjecture and Gaiotto conjecture mean in the case of GRMN, F4, and OST 2K2L. And to make it more precise, but first let me have a look. What is time? Great. Yeah. So, okay. So first we have GLMN case. For the GLMN case, to start with, let us start from the case when n goes to n-1, because we don't need to introduce many notations in this case. In the case when n equal to n-1, our G, that is GL n minus 1 times GL n, and your H, that is GL n minus 1, and the C is 0. So your hyperspherical variety M, it is just the yeah. So yeah, H it can be invited into G diagonally. Here it is this, and this one also this. Yeah. So your M it is the classical non-twisted codation bundle on G equals to H, which is just the codation bundle on GRN. So that is the left side, your G and M. Its hyperspherical dual. It is given by this, where your G check, it is still GL n minus 1 times GL n, and your M check, it is the potential bundle on the whole space from Cn minus 1 to Cn. So under this hyperspherical duality pair, your BZ-SV conjecture, or the implicit conjecture, it says the category of GL n minus 1 F equivalent the modules of the Grassmannian associated with GRN minus 1 times GRN, because here GRN minus 1 it is H here, and GRN minus 1 times GRN it is your G here, and this is your left side, which is just definition equivalent to GRN minus 1 O equivalent modules on the Grassmannian associated with GRN. So that is your left-hand side. And the right-hand side, it is just the category of representations of the degenerate supergroup associated with GRN-1n. So that is untwisted case. For the twisted case, it means the Gaiotto conjecture, it says the follows. It says when kappa is generic, then GL-1O equivalent kappa twisted modules on the Grassmannian, it is equivalent to the category of representations of the quantum supergroup associated with GRN-1n. So that is a statement of our conjectures. The conjectures of Ben-Zvi and Gaiotto.
So is it possible to, I don't know, it's me.
Yeah, sorry.
Yeah, to see some explicit response. I don't know, take some representation.
Yeah.
And irreducible go to irreducible? Do you mean?
No, like some non-representation of GLN minus 1n. And what's the corresponding development?
Roughly, there are discretely many orbits of this GLN minus 1O on the Grassmannian GLN, which is surprising. And roughly, they're just in bijection with reducible representations of the quantum supergroup. That's not quite true. I mean, some orbits in the left-hand side do not carry any equivalent D modules, and they're called irrelevant. But the relevant orbits are in nature of bijection with irreducible finite dimensional representations in the right-hand side.
Yeah, for irreducible objects on the representation side, you can consider they correspond to the IC extension of some local system on the orbit on the left side. I mean GRN-1O orbit in the Grassmannian. For each of them, you consider the rank 1 local system on site, and then you consider the IC extension. So that is what does the irreducible representation they correspond to. So that is the statement of the conjecture, and it have already become theorem for the untwisted conjecture. It had already been proved by Braverman, Finkelberg, Travkin, Ginzburg. I always make a mistake about alphabet. Ginzburg and Travkin. So that is for the untwisted case. And for the twisted case, it has already been proved by the Braverman and the Finkelberg and the Travkin. So that is the case of m equal to n minus 1. Actually, in BFGT and BFT, the authors also proved, or using a similar proof, you can prove the case when m equal to n case. For m equal to n case, your G, it is GLN times GLN. And your M, it is T star GLN times AN. and its hyperspherical field, it is given by this, where your G check, it is still GRN, times GRN, and N check, it is T star, home, CN, CN.
It's making because the even odd part of the supergroup.
Yes, yeah, uncheck it is a even part, sorry, this one it is the even part of the supergroup, and this one it is the odd part of the corresponding superalgebra. So in this case, the Gaiotto conjecture, the intrinsic Gaiotto conjecture or BZSV conjecture, and the Gaiotto conjecture, they say the following thing. It says that GLN O equivalent the modules of the Grassmannian associated with GLN, maybe let's see BZSV. Times Fn, it is equivalent to the category of repetitions of the degenerate supergroup corresponding to GLN, and it has already been proved due to the FGT. And also the twisted version and the Gaiotto conjecture, in this case, it says the GL and O equivalent kappa twisted modules are the Grassmannian associated with GRN times Fn. It is equivalent to the category of representations of the quantum supergroup associated with GRNN. And it can be proved using a similar proof in ESP. Okay. Yeah, so maybe it is the alarm to mention, to alarm you to make it more, to make it faster. That is a case of m equal to n minus 1 case and m equal to n case. Now let us introduce the general conjecture, the general case, which means we put a condition that, okay, so for general m smaller than n, then we need to introduce some notations now. We let UMN be a unipotent subgroup in GLN, which is the unipotent subgroup corresponding, it is a unipotent radical of the parabolic subgroup of GLN corresponding to the partition n plus 1, 1. So if we write it more explicitly using the matrix, then it is of the following form. So here it is your UMN, and on the left top corner there is m plus 1 times m plus 1 block, which is just identity here. So that is your UMN, and you regard it as a subgroup of GLN. And then you notice that you can invite your GLM into your GLN, which is just given by inviting to the left top corner, and because you notice that there is m plus 1 times m plus 1, and you can invite your GLM to the first m many rows and columns. Yeah. So this way, you regard GLM as a subgroup of GLM, and you have a conjugate action of GLM on your UMN. So in particular, you can form a subgroup H of GLN, which is by definition of GLM semi-direct product with UMN. And also your group H, it has a character denoted by a C, an additive character from H to A1, which just sends a matrix of the, first, if H we can write it more explicitly as this. The left top corner, there is GLM, and on the right part, there is UMN, and there is a column in the middle to separate them. So it is your H. The character per C, it is done by taking sum of entrance in the subdiagonal which belongs to the UMN area. This part, this thing. So to be more precise, it sends H to sum of HI, I plus 1, where I goes from n plus 1 to n minus 1. So that is your C. After we introduce these notations, we can formulate our hyperspherical varieties and its dual hyperspherical variety. Namely, your G, it is GLM times GLN. And your H, it is just H. And the C is the C. So your T star, so your M, it is a perceived twisted potential model on G quotient H, which is the same thing as the perceived twisted on GLN quotient UNN. So that is your hyperspherical variety. Its dual hyperspherical variety is given by this, where your G check, it is GLM times GLN, and your M check, it is the cotangent bundle on home CMCN. So through this way, now we can formulate the untwisted Gaiotto conjecture or pediatric conjecture and the twisted Gaiotto conjecture. For the first, EDS3, it just says the category of HF, the C equivalent modules of the Grassmannian associated with GLM times GLN, which is just equivalent to the category of a GLMO, semi-direct that with UNN, F, the C equivalent modules of the Grassmannian associated with GLN. It is equivalent to the category of representations of the degenerate supergroup correspond to GL and N. And for the Gaiotto conjecture, it is twisting. It says GLMO semi-direct product with UMNF, the C kappa twisted modules of the Grassmannian associated with GLN, which is equivalent to the category of representations of the quantum supergroup. Kappa generic. And the above two conjectures will also become theorems. For the BZSV conjecture, when m equals to 0, it has already been proved by Frankel, Ginzburg, and Willman. And for other cases, when m bigger than 0 and smaller than n minus 1, it has already been proved by Travkin and yeah, in 2022. And for the Gaiotto conjecture, the twisted version above, when m equal to 0, it is proved by Ginzburg. And when in other case, when m bigger than 0, smaller than -1. It has already been proved by Travkin and Yang in around 2023. So that is the case of the Gaiotto conjecture for M, for any M case. So that is all the cases. Yeah, so that is the GRM case. Then let us mention the M4 case. For M4 case, first let us mention the group PSP6, and we have a unipotent subgroup U prime belong to a subgroup of PSP6, which is if we write it very explicitly as 6 times 6 matrix, then the U prime here, it is concentrated in this area. Yeah, so that is your U prime. And you regard it as a subgroup in PSP6. And you notice that your PGL2, it can invite into PSP6 diagonally. I mean, you can regard your you can invite your PGL2 to something like 2, 2, 2. I mean, 3 copies. And then you regard it as subgroup in PSP6. And through if you regard PGL2 in this way, you have a conjugate action of PGL2 on your U prime. So you can form a subgroup H, which is defined as PGL2, then double that with U prime. And you have an additive character from H to A1, which sends H to H13 plus H24. So through this way, you can formulate a hyperspherical variety. Your G, it is PGL2 times PSP6. And your H, it is this H, your P is this P. So your M at a T star on the quotient G by H, which is then by this. And the twisted potential bundle on PSP6 quotient U prime. That is the hyperspherical variety on the left side. If you consider its due hyperspherical variety, it is done by this. We are G-check. So SL2 times spin 7. And your M-check, it is the standard representation of SL2 tensor with the 8-dimensional representation, spinor representation of a spin 7. So that is your dual hyperspherical variety. And now the conjecture is that the PGL2O semi-durable that with U prime alpha, the C equivalent modules of the Grassmannian associated with PSP6, it is equivalent to the category of representations of the degenerate supergroup corresponding to I4. And the Gaiotto conjecture is that the PGL20 centered by the way U prime alpha to C equivalent hyperalgebraic modules of the Grassmannian. It is equivalent to the category of representations of the quantum supergroup, the Hyperalgebraic. For the first conjecture, we still don't know. But for the second conjecture, it is almost proved and will appear in the upcoming work of
just exclude F4 is an exceptional supergroup and check exact account even an odd particle.
Okay, so yeah, Roman just said for F4, its even part is this. It's the odd part of the least algebra is this. Yeah. Okay, so it will appear in the upcoming work of Finkelberg, Travkin, and yeah. So that is the case of F4. Let's see how many minutes left. Okay, 12 minutes. Yeah. Okay, so yeah. And so we can just finish mention the OSP case. We consider the case of OSP even, 2K12 that we denoted before. To start with, let us consider the case where 2K it is 2n and 2L it is 2n. Because as before, in this case, we don't need to introduce the unipotent part. For OSP 2n to n, in this case, your G, it is SO to n times SO to n plus 1. And your H, it is SO to n. And your M, it is a potential bundle on G quotient H, non-twisted. So that is SO to n plus 1. And its due hyperspherical writing, it is given by G-check. G-check it is SO2n times SP2n. And your M-check, it is the product of standard representation of SO2n and the standard 2n representation, 2n-dimensional representations of SP2n. And this. So the conjecture is just as the category of SO to NO equivalent modules on the Grassmannian associated with SO to n plus 1. It is equivalent to the category of representations of OSP and the line to n to n. That is the untwisted conjecture, and for the twisted conjecture, it says SO2NO kappa twisted modules on the Grassmannian. It is equivalent to the category of representations of the quantum supergroup. this conjecture, both of conjectures, they have already been proved. For the first conjecture, it has already been proved by BFT, and Braverman, Finkelberg, and Travkin. In around 2019. And the second conjecture, it can be proved using the same technique as the work of BFT in 2021. Yeah, so now let us mention the general case. For the general case, let us mention some examples. Let us first introduce some numbers. We take the minuscule m, such that 2m plus 1 no more than n. And we set m to be n minus 2m plus minus 1. So that is your big M. In this case, you can invite your SO n plus 1 into SON, which is given by this. I mean, you think your SO n plus 1, you can invite into the middle part of SON, just exactly in the middle. Here it is M, and here it is M. And also, you can consider a unipotent subgroup U, tutor, and N belong to SON. Which can be written down like this. There it is m plus 1 times m plus 1 part in the middle, but you don't have anything here, I mean just the identity. Your U tutor and N is this. And the unipotent concentrated in this area. Yeah. So if you give an isotropic vector belong to Cm plus 1, then from there you can determine an embedding from SOM go to SOM plus 1. So through this way you can realize SOM as a subgroup of SON. And also even from there is some procedure to get a character C, an additive character C on SOM. Then therefore that UMN tutor to A1, which is denoted by H. Then we can formulate our hyperspherical writing where your G, it is SOM times SON, and the H, it is this H, for C it is for C, and your M, it is T star to C on C quotient H, which is just equivalent, isomorphic to, for C intrinsic quaternion bundle on SON quotient UMN tutor. Yeah, and similarly, you consider the corresponding hyperspherical writing. And then the conjecture, it just says the following thing. It says the category of SOMO semi-direct that with U tutor and N F for C equivalent modules on the Grassmannian associated with SON it is equivalent to this thing. The first case, it is equivalent to OSP underline m minus 1. If your m is odd. And also, in the case when your m is even, then it is equivalent to the category of repetitions of OSP underline n minus 1. And so for this conjecture, only the case when m is very close to n, it is known due to BFT. And in the case when 1 of m or n minus 1 or n or n minus 1 m minus 1 equal to 0, only this special case it is known. Other cases is still open. And then for the Gaiotto conjecture, when we consider there is a twisting kappa is generic, you need to replace it by the category of repetitions of the quantum supergroup. Then in this case, when m is very similar to n, it has already been it can be proved using the same technique as a BFT 21. Yeah, and when m very similar to 0 or n very similar to 0, it can be proved using the same technique as a category. For paper. And for other case, it can be proved using the same technique as Travkin and Young in 2023. So that is the case of OSP to be 12. So maybe let me stop here.
Questions?
So in this conjecture, Ben-Zvi-Sakellaridis-Venkatesh and
Yes.
Gaiotto, what about monoidal properties of this equivalence? Do you expect them to be monoidal in some way?
Yes. I mean, on the left side, on the representation side, you have a tensor product for the representation category, and on the left side, you have some monadal structure given by fusion product, by the fusion monadal structure. It comes from the factorization structure, and it matches. The monadal structures they match.
So what is this En for what n?
E2.
E2.
Yeah.
Even in Ben-Zvi-Sakellaridis-Venkatesh before quantization.
Sorry.
Even in Ben-Zvi-Sakellaridis-Venkatesh, this is only E2.
No. I think on the left-hand side, in this case, you can
I'm not sure. I'm not sure it can be promoted to infinite.
Yes, we do not because. And the proofs.
It's
and this proves, you mentioned that this conjecture proves in some cases, and in these cases you know that this is the equivalence of E2 monadal categories.
Yes, I mean, like braided monadal categories.
So in this case, there are also some other convolution operations on the nerves and cells.
Mm-hmm.
So
So you're mentioning that there are different monadal structures.
For GL and
Three?
different
Yes.
but yeah, I don't know. Well, generalize this to other groups.
Mm-hmm.
Duality between relation correspondences and between hyperalgebraic.
In general, as far as I understand, due to the work of Finkelberg, Dillon, Travkin, Braverman, and others, about column branches and all that, we have a general definition of dual hyperspherical variety, yes?
Uh-huh.
So both sides of both categories in these conjectures, in this conjecture, are well defined already. Or are they conjectural?
Sorry, I don't.
It's a question of
Generalization.
what is the precise definition of a hyperalgebraic?
Well, maybe I probably know what is precise definition of. So do you at least have a comparison functor, like derived Sataki equivalence? You can at least construct a comparison functor starting from say abelian Sataki. Do you have some at least comparison functor in this in the general case, or is it?
You mean to the web?
Say
What do you mean by comparison functor?
you have two categories which you hope to prove.
Sorry, we have what? Two what?
Two categories
Yes.
in question.
Okay.
The problem is, Artem means that there is some function from one category to the other.
Some natural one, or is it?
So description naturally defined function for one to be able to effectively equivalent.
You mean for general hyperspherical duality?
Yeah.
I don't know.
In the untwisted case of the whole category is generally from the use of by the society action itself, but definition is to define the dual one as the equivalent and the morphism to the comprehensive invasion from the right-hand side to the left-hand side.
But if you consider the action of the action of the static category on your category, then the object that you can, the category that you obtain, it is in some sense semi-simple, right? It is.
But generally, in the end, take all the continent steps.
I see, got that.
For the sub.
But are you sure that it can? I mean, these extensions they match with the partition side.
I think you could ask. You can do this the left and the morphism. What do you know? After all, you might not know much about your expected to be concentrated even formalizable ways and pure or something. And the functions draw that variety. But in this definition, I think is not at all automatic on the definition.
Mm-hmm.
So in short, the answer is yes. Good.
Okay, we can discuss later, right?
But this does not help me. So there is a corresponding, but often used.
Well, it's hard to compute this de-currentize internal form.
And you need to, like, sort of in each concrete case, it is some new ideas.
Yes. For example, in this four case, Ruotao mentioned, as he said, it is possible to prove that the Gaiotto will not have conjecture, but we're not able to compute this internal